And it's code in the D to give the keyboard a punch. Then cross, correlate, and a break for some lunch. Correlate, tabulate, process, and screen. Program, print out, regress to the mean. And it's, oh boys, can't you code it? Program it right. Nothing ever happens in the...
In today's video, we're going to look at how to use Stata to calculate or estimate regression models. There's good news about the regression command. It's very simple. There's not too many options. In fact, we'll spend most of our time talking about how to use factor notation in Stata to estimate models with dummy variables or indicator variables and interaction terms. There's a couple of different kinds of interaction terms. We can interact a discrete variable with another discrete variable. We can interact a discrete variable with a continuous variable, or interact two continuous variables. But I'll show you the language of how to do this in Stata with great ease, and then this builds the foundation for a more complicated topic, which is about post-estimation in regression and using things like margins and margins plots. So you can see in the background I've already got Stata up and running. I've loaded the general social survey, and the first 3 lines of my program code I've gone and taken a subset. I've restricted my data to 2010 and just kept a handful of variables. Also, the race variable has 3 categories. I've dropped anybody who's coded as a category 3, which means other. So let's go ahead and look at a couple of quick commands here. First thing I'm going to do, our major dependent variable for this example video is going to be prestige 80, which is occupational prestige based on 1980 Dictionary of Occupational Titles. I'm going to go ahead and summarize that variable right here. And we can see that how many observations we have, our arithmetic average, standard deviation, minimum, and maximum. So this variable ranges from 17 to 86. It has a mean of about 44 and so forth. The first thing I'm going to do is show you that the regression command, you've probably learned this in a stat class, but that regression and calculating arithmetic averages are related to each other. In fact, the arithmetic average is really a simple, a special case of regression. So down here on line 7, I'm going to highlight my command, which is regress, followed by my dependent variable. Notice that I don't have any independent variables here. So when I execute this by clicking on this button over here, the execute selection button, I get my regression output, and we can see in the regression output there's 3 areas of interest here. We get an ANOVA table, which when we don't have an independent variable is really not too important for us. We get a table, a model summary table, which has things like our R squared and our F statistic, and then we get our table of coefficients down at the bottom. So Stata pretty routinely, if you don't take any other defaults, you'll always get those 3 pieces of information. The thing I want to point out here is that our regression coefficient, our beta hat sub 1, actually in this case beta hat sub 0, is the same value as the arithmetic average from the summarize command. So we can go ahead and I'll just add another variable in here. If we move down to line 11, you can see now I'm going to highlight this line. We're going to use the regress command. We're still going to have our dependent variable be the occupational prestige variable, but now we'll add another continuous variable which represents the father's occupational prestige. And we're going to look at the relationship between father's occupational prestige and the respondent's occupational prestige. And when I execute this, I get my very typical regression output. We're not going to spend a lot of time going through the interpretation of this output, but again, you can see that you get an ANOVA table, and that the ANOVA table is laid out so we can calculate the ratio of the 2 mean squares, the mean square model to the mean square residual, and that's given distributed as F. And that model summary statistic is given in the next panel, where we see our F statistic, which is quite large, and our associated p-value. And then in the bottom panel, we see we now have 2 coefficients. We have our intercept, beta hat sub 0, which in Stata is given as underscore CONS. That's the name that Stata uses for that. We have our beta hat sub 1, which is POPRES 80. And we can see that for each additional 1 unit increase in father's occupational prestige, there's a beta hat sub 1 unit increase in respondent's prestige. Our R squared is not very large for this particular problem, indicating that there's a weak relationship, even though it's statistically significant, a weak relationship between father's occupational prestige and respondent's occupational prestige. So moving on, I'm going to show you two options that are, you may never use them, but I'm going to use them in this video, particularly the no header option, because what it does is it reduces the output. So here we have three different, in our typical output, we have three different sections: the ANOVA table, the model summary statistics, and the table of coefficients. If I use the no header option, this will remove those top two panels. It'll just give us the table of coefficients and won't give us the ANOVA table or the model statistics. If I use the no table option, it will give us the ANOVA table but not the regression coefficients. Now, typically I don't use these. I look at the output you see here. But for like making this kind of a video, or if I want more things to fit on the screen, the no header option is actually very nice to have, because I'm not particularly interested in the ANOVA table or the model statistics. When I'm more interested in the coefficients, I can get more on the screen. Let's go ahead and see what, I'm going to execute both of these commands and see what we get. So here you can see that my first command produced the table of coefficients, no ANOVA table. And then the second command produced the ANOVA table, but the ANOVA portioned the header of this output, but didn't produce the table of coefficients. So feel free to use those. You'll see that I'm going to use them pretty much, the no header option, pretty much for the remainder of this tutorial video. Let's move down a little bit. So there's an option in, again, in your statistics class, you probably learned about the difference between a regression coefficient and a beta coefficient. The beta coefficient is a standardized coefficient. It's as if all of the variables in your model, both the dependent and all the independent variables, have been converted to standardized scores, like a z-score, and you've regressed the z-score of the dependent variable on the z-score of all of the independent variables. Then your regression coefficient ends up being in a standardized metric of z-score units. So a 1 unit change in x really means a 1 standard deviation unit change, and the beta hat sub 1 unit change that you see in your regression coefficient is also measured in standard deviation units. The option to go ahead and calculate this is the beta option. So if we look down here at lines 19 and 20, you'll see line 19 now I've built a slightly larger model. We're going to regress occupational prestige on father's prestige, respondent's education, and father's education, and I'll suppress the ANOVA table. And in the line right underneath that, I'm going to estimate the exact same model, but I'm going to use the beta option, and so we'll get our beta coefficients. If I'll highlight both of these lines and execute, now we look at the output, and you can see the difference. So for Stata to produce the beta coefficients, it had to get rid of something to make room on the screen, and Stata doesn't provide for you the 95% confidence intervals for the regression coefficients when you use the beta option. But if you're interested in, if your modeling exercise is to determine which variables are the most important, and if they're measured in different scales or different metrics, then the beta option is something you want to explore and look at and possibly use to see which are your most important variables in your model. We're going to move on now and look at dummy variables. So Stata has something called factor notation, which allows you to create dummy variables and interaction terms on the fly as you specify your regression model. And it's very powerful, and I definitely encourage you to spend some time figuring this out. It's really going to be helpful when you want to calculate margins, marginal effects, and plotting your results. And we'll have a video to cover this a little bit later. But for now, I'm going to show you kind of an old school way of doing this. So let's look at the code that begins in line 24. First thing I'm going to do is I'm going to generate a new variable called sexDum, and I'm going to assign it equal to sex equals 2. Now that sex equals 2 will be evaluated as either true or false, and in Stata, true equals 1 and false equals 0. So this command is going to selectively change the value of sexDum to 0 or 1 depending upon if sex is equal to 2. That's going to create a dummy variable for us. I'm then going to define a label, and then I'm going to assign that label to this new variable, and then we'll look at a cross tabulation of this new variable sexdom with the variable sex, and I'm going to suppress the labels so that you can see that 1 and 2, which are male and female in the sex variable, have been recoded to be 0 and 1. By the way, this cross tabulation is not a bad way to check your recodings to see that it's done exactly what you want it to do. So we can see there's no cases in the off diagonals. My coding scheme didn't miss anybody, and that sure enough, on the sex variable, the 1 has been coded to 0 and the 2 has been coded to 1. So now I have a nice dummy variable, and I can go ahead and run my regression analysis. I do that in line 29 here, and I'll just run this one example. And again, we're going to regress the occupational prestige measure on father's prestige, and then we're going to add this additional variable for sex dummy, which is going to really give us a difference of means t-test comparing men to women after adjusting for father's occupational prestige. Here's our output. You can see that our coefficient is about 0.15, indicating that there's about a 0.15 difference between men and women on occupational prestige after adjusting for father's occupational prestige. We have a very small t-statistic, and our p-value is large, so we fail to reject the null hypothesis. We're not finding any gender effects here. But I do want you to look at that coefficient, 0.15. Now let's go ahead and use Stata's built-in factor notation to estimate the same model. In the next line, line 30, you can see that I have the same model, but instead of using the sexdom variable I created that took 4 lines of code to create and to evaluate, that just in my command stream, I'm going to use my original sex variable and state it as I.sex. I means that it's going to be an indicator variable. Now in this case, I know that the sex variable has 2 values, and that 1 is equal to male and 2 is equal to female. By default, when I use I.sex, I will get 1 dummy variable, 1 indicator variable, with the group coded 1, the lowest coded group, that is the men, will now be equal to 0, and that the higher coded group, women, which are equal to 2, will be coded as 1. Stata will do this for me automatically. And I should get exactly the same results here that I got in the model above. And it's a lot easier with a lot less lines of code. So you can see my output changes a little bit, that I get a little bit extra notation, and it's telling me that under the sex variable that female is the group coded as 1, and in fact I get the exact same coefficients, which is what we expect. Now, you've also learned in the statistics class that with a dichotomous dummy variable, it's arbitrary which group you code as the excluded or 0 group, the reference or base group. In this case, I've done it both times, coding men as 0 and women as 1. You may prefer to have that be the other way, to have the female group be the reference or baseline group, and the male group be the included group. So you can use factor notation to change that. And if you look at the next line of code, line 31, you'll notice that I have a little snippet of, so instead of having I.sex, I now use IB, and in parentheses, I put the value of the category that I want to be my omitted group listed there. So I have IB2.sex. And the outcome of this should be that I get exactly the same regression results. And while I'm not showing you the ANOVA table, the ANOVA tables for these 3 models will be identical. The coefficients, the absolute values of the coefficients will be identical. The only difference here is that the sex variable, the coefficient will change direction. So it's been positive in the first 2. This one should end up being negative. Same number, but negative, and there it is. And now you can see the label has changed to indicate that the group coded 1 is male, not female. It's a great feature in Stata. Learn how to use this factor notation for dummy variables. Now, when we have a discrete variable that has more than 2 categories, so here we have academic degree. The academic degree variable has multiple categories. It starts at less than high school and ends up with graduate education. So it's a discrete, orderable variable with more than 2 outcomes. So we can again create a series of dummy variables, and in your stat class you've learned that if you have, say, 5 categories of a variable, you would need to create 4 dummy variables, at least 4, but you could include no more than 4 in your model, and the variable you leave out represents your baseline or omitted group. So again, to do this longhand, kind of in an old-fashioned way, I can create a set of dummy variables. This is not the way I prefer to do this. I'm going to use factor notation virtually every time, but I just want to make certain you understand how to create those dummies and that you get the same results if you do it this way. So in this case, on line 35, I'm using the tabulate command, and we've covered this in other videos. We know that tabulate will give us a one-way frequency distribution of a variable. But I'm also using here the generate option, and so it's going to take each category, each outcome of that variable, and create a dummy variable. And it's going to use degree as the prefix to that variable. So it's going to create a couple of new variables for us. Let me go ahead and run this, and then we will tabulate all of those variables. And that, notice that I'm using tab 1 so that I can do multiple frequency distributions, and that the degree is the prefix. And what Stata will do when it creates these new variables, it will add numbers 1, 2, 3, 4, 5, and so that question mark is a wildcard that says match any single character or number here. Let's go ahead and run this. So you can see if I scroll back up here a little bit, it doesn't really matter where we start. Here's our degree variable, less than high school, junior college, bachelor, and graduate. I know that from using the GSS for a while that less than high school is coded 0, and then it increments by 1 for high school, 2 for junior college, and so forth. Using the generate option for tabulate, it's now created a whole series of dummy variables for me, and they're each coded 0 and 1. That is, you either have achieved that academic degree, you're coded a 1, or you have not, you're coded a 0. And you can see over in my variables list over here that these variables have been added to my data set. If I save my data set now, next time I come back they'll be here for me to use. So let's go ahead and look at our regression model. So regression model number 1 here in line 37 is to regress the prestige variable on J-1 dummy variables. Notice I've left the degree 1 variable, which is less than high school, out of this model. Let's look at the next line of code, line 38. This will produce the exact same regression output, but here I'm using the I.degree, or the factor notation for the degree variable. And it will produce exactly the same because when Stata creates these, automatically creates these dummy variables for us, it'll take the value, the lowest value, which in this case is less than high school, and automatically make that my omitted group. I can also use the IB notation, and you can see that in the next line, in line 39, and I can say, for example, IB4.degree, which will take my last group, the graduate degree group, and use them as the omitted group. So let me go ahead and highlight these 3 lines of code. Here's what I expect to have happen. The first 2 regression estimates should be identical. The third should omit the graduates, people with graduate degrees, and kind of flip the relationship. Now, one of the advantages of using the factor notation, you can see in that second model, is that it keeps the value labels for me. So I can see my coefficient for high school, junior college, bachelor degree, and graduate, where when I do the dummy variables, creating them on my own, I just have degree 2, degree 3, and degree 4. When I create my own dummy variables like that, or I should say when I used to do that before factor notation, I would typically add more lines of code to rename those variables so that they would be meaningful in the regression output. And then if you look at the bottom regression, you can see that my, again, the 3 ANOVA tables, which are not displayed here, are identical. My constant is different because that's now the value of the excluded group, which is the average occupational prestige for people with graduate degrees. And all my coefficients have become negative to reflect that all the other educational groups have, on average, less occupational prestige than the graduate degree group. So you have total control over how you do this. If you're using factor notation, you can either let Stata omit the lowest valued group, but that may not be what you want, in which case you have to use the IB form of factor notation so that you can specify which group you want to exclude. Again, you should consult a statistics text or your class for a discussion of how to select the variables to use as your base group. My last example is going to show you how to create interaction terms. As I said at the beginning of this video, you can interact any kind of variable. You could interact two discrete variables, you could interact a discrete variable with a quantitative variable, or you could interact two quantitative variables. In fact, it's often typical to interact a variable with itself. For example, in the relationship between income and age, that tends to be a nonlinear relationship. The rate of increase of income goes up as people age, but the rate of increase begins declining around age 40 and eventually turns and becomes negative. The rate of increase decreases when you get to about age, say, 55. That is not well modeled without an interaction term of age interacted with itself. That is a quadratic. But having said that, the simplest way of doing interaction terms in Stata is to go ahead and use their factor notation. So let's go ahead and look at three different models down here, starting on line 43. Again, our typical regression here is we're going to regress occupational prestige on father's occupational prestige. We're going to use a dummy variable for race and a continuous variable for education. There's no interaction term in that first model. Our second model, we're going to use factor notation, but it's a bit of a longhand way. So the last two models are identical. I prefer the last model because it's just less typing, but some people like that model on line 44 because it reminds them that they need to put the main effects in the model. So here's how you use the factor notation to do an interaction term. We're going to regress occupational prestige on father's occupational prestige. We're going to have race, but we're going to declare that it's a factor variable, so it's I.race. We're going to have education, EDUC, and at that point, those are our two main effects. Then we're going to specify an interaction term, which is I.race, and then we have a pound sign, C.educ. Now, we've been using I for categorical variables. When we have continuous variables, particularly in the interactions, we have to let Stata know that they're continuous, and instead of I dot, we use C dot. And then finally, in the model on the last line of the program here, I can shorten the main effects and the interaction effects by simply specifying the interaction I'm interested in, I.race and then C.educ, and connecting them with two pound signs. Two pound signs says I need the main effects, that is, I need to have race and education in my model, and then I also want you to include the interaction effect. So let's go ahead and look at these three models. So our top model, no interaction effect. We can see that the race coefficient is negative and statistically significant. The education coefficient is positive and statistically significant. The last two models are identical, so it really doesn't matter which one we look at, but we can see now that father's occupational prestige is positive and statistically significant. The race variable, the main effect, is not significant. The education variable main effect is statistically significant. And then we have our interaction term for race, which is also not statistically significant. So in this particular example, the interaction effect doesn't pay off for us, and we'd probably want to select a more parsimonious model and get rid of the interaction term and just look at the main effects of race and education. Well, I hope this gets you up and running with regression, particularly if you have access to something like the General Social Survey. You can now begin estimating models with great ease, and it's really kind of a fun little bit of joy to go out there and play with these models and be able to discover things in the social world quite easily. We're going to have more videos on post-estimation commands, and that's really a trickier area. There's a lot more things going on, but I'm going to give you advance warning. You need to look at the margins and margins plot sections of the manual. You're going to benefit greatly from knowing how to use those two post-estimation commands. They will make your life very much easier for your statistical life, and you'll be able to interpret your results better because you'll have great visualizations of the computer output. As usual, if you have any questions, let me know and I'll do my best to answer them.
And it's code in the D to give the keyboard a punch, then cross, correlate, and a break for some lunch. Correlate, tabulate, process, and screen. Program, print out, regress to the mean. And it's, oh boys, can't you code it? Program it right. Nothing ever happens in